All right, in this video, I'm going to talk about some of the problems that you might see in the homework in section 5.5 in my math lab. Section 5.5 deals with the substitution rule, where you have to find an appropriate substitution for your integrals. Like in problem number 1, we got the integral of cosecant square of x divided by the cotangent to the fourth of x dx. All right, in this case here, I'm going to bring over the integral sign and then cosecant square of x. Now, cotangent to the fourth of x, I'm going to rewrite that as cotangent of x raised to the fourth, and then dx. Now, in this case here, I'm going to try to find an appropriate substitution where I can get the derivative of that with respect to x. Like this one right here, the cotangent of x in the denominator. The reason why I wrote it like this is because I'm going to let u equal to the cotangent of x. And I know something about my the derivatives of the six trigonometric functions here. If u is the cotangent of x, then that means du, its derivative, will be negative cosecant square of x dx. Now, you might want to refer back to, I think, section 3.5 when we talked about the derivatives of your six trigonometric functions. Be familiar with those. Okay. Now, I got cosecant square of x dx, but here I got negative cosecant square x dx. Well, if I want that to be the same as this, when I do my substitution, I need to divide both sides by -1. Or I could multiply both sides by -1. So it'd be negative du equaling to cosecant square of x dx. Now I can do my appropriate substitution here. Here cotangent of x would be u, whereas cosecant square of x dx, that's going to be negative du. So here's what I have. The integral of negative du over, this will be u raised to the fourth. And also I got the negative, that's like -1, so I can pull that negative sign on the outside. So this will be the integral of that u to the fourth. In the denominator, if I pull that out of that denominator, it will be u to the -4 du. And then bring down the negative sign and just integrate u to the -4 du. So in this case here, using the power rule, I increase the power by 1, so it will be u to the -4 plus 1, that's -3, divided by that new power of -3, and then plus c. Now, of course, negative divided by negative will be positive, so, and I got that 3 in the denominator, I'll write that as 1/3. And also that u to the -3, I can write that in the denominator as 1 over u cubed plus c. So here I got 1/3 times 1 over. Now the u, I'm going to do the back substitution. U was the cotangent of x, so this will be 1 over cotangent of x. That would be to the third power plus c. And then I'll bring down this 1/3. The reciprocal of the cotangent, that's going to be actually the tangent of x. 1/3, the reciprocal of the cotangent of x is the tangent of x. You might want to refer back to section 1.4 dealing with the reciprocal identities for your trig function. So one of the cotangent will be the tangent of x, and that's cubed, plus 3. And then 1/3. Tangent of x raised to the third, another way of writing that would be the tangent cubed of x, plus c. Okay. So this right here is the integral for the cosecant of x, cosecant square of x divided by cotangent to the fourth of x dx. 1/3 tangent cube of x plus c. Okay, here's another example. Now this one has the natural base e in it. So let's say you had something like this one, the integral of e to the 8x divided by e to the 8x plus 2 dx. So in this case here, what I have to do here is I'm going to let u be the entire denominator. So pretty much you have to try something in order to hopefully get what you're going to want to use here, in this case here, to get the right simplified integral. So if I let u be that denominator of e to the 8x plus 2, then du would be, well, of course, the derivative of e to whatever is going to be e to whatever. So this will be e to the 8x plus 2. But I have to use the chain rule by taking the derivative of 8x plus 2, which will be 8 dx. Okay? You want to make sure that you apply the chain rule on this particular problem here. The derivative of e to the 8x plus 2, that's this e to the 8x plus 2, and then you have to take its inside derivative of that exponent. Derivative of 8x plus 2 will be 8. And now we got this with the dx, but I want the e to the 8x plus 2 dx by itself. So I need to divide both sides by 8. So I know I got 1/8 du is equal to e to the 8x plus 2 dx. I'm sorry, this 2 should not be in the exponent. In other words, this 2 should not be in the exponent. It should be just e to the 8x and then multiply by this inside derivative, which is 8 dx. So this will just be e to the 8x dx, equaling to 1/8. Okay. The derivative of that 2, which is the derivative of a constant, that's 0. So that's the mistake that I made here. Okay, so now we can do our substitution here. This e to the 8x plus 2, that's going to be the u. E to the 8x dx, which is what I have here, that's going to be 1/8 times du. So now we're going to have this, the integral of, that numerator is going to be 1/8 du divided by the denominator, that's u. The 1/8 will go on the outside, so it'll be 1/8 times the integral of du divided by u. And the integral of du over u would be the natural log of the absolute value of u plus c. And then we do the back substitution by replacing that u with e to the 8x plus 2. So it'll be 1/8 times the natural log of e to the 8x and then plus 2. And keep in mind that plus 2 is not part of the exponent in the e. Okay. So that's what the integral of e to the x divided by e to the x plus 2 dx will be. 1/8 natural log of e to the 8x plus 2 plus c. Notice I have the absolute value there, because that could be negative. All right, problem number 3. Here's another example of just that. Well, just another example. Let's see. In this one, we have definite integrals here. That's going to be the integral from 0 to 1 of x cubed times the square root of 1 minus 4x, 1 minus x to the 4th dx. Okay, I'm going to show you how to do this one where you can change your limits of integration. These are for the x's. I can change them to be limits in terms of u. All right, so here's what we're going to do. I'm going to let u equal to what's underneath the square root symbol, 1 minus x to the fourth. That would mean du will have to be this. The derivative of 1 is 0. The derivative of negative x to the fourth would be negative 4x cubed dx. Well, I got the x cubed and the dx, and maybe I could rewrite this so you can see what I'm doing here. Integral from 0 to 1 of, put the square root of 1 minus x to the fourth in front, and to the back, x cubed will go along with that dx. So you can see I do have x cubed dx here. But let's let this be, make this x cubed dx by dividing both sides by negative 4. So I'm going to have a negative 1/4 equaling to negative 1/4 du. Yep, negative 1/4 du is equal to x cubed dx. All right, now I'm also going to do this, change my limits of integration from 0 to 1, and I'm going to have them in terms of u limits, because I know what u is by the way. So in this case, all right, here's what we're going to do. We got u equaling to 0 and u equaling to 1. Those for the limits for x. Let's put them in terms of u. If, not u, in this case, it's just x. These are limits for x. I'm trying to get them in terms of u. So actually, x equals 0 means that u is equal to 1 minus, I'm going to replace the x with 0, so 1 minus 0 to the fourth ends up being 1. And then for x equaling to 1, that means u is equal to 1 minus, my x is 1 to the fourth. 1 to the fourth is 1. 1 from 1 is 0. All right, so now my lower limit is 1, and my upper limit is 0. So that 1 minus x to the fourth, that's going to be the u. X cubed dx, that's negative 1/4 du. And then I'm going to change these limits from 0 to 1 to 1 to 0. So this time, the integral from 1 to 0 of u times negative 1/4 du. And you know what I'm going to do here? My limits here are from the largest to smallest. It's got to be from smallest to largest. So I need to switch these limits of integration from 1 to 0 to 0 to 1. But if I do that, I got to put a negative sign in front of it, because this will represent the opposite of this. So the negative sign goes there. And I'll rewrite this as u times negative 1/4 du. And I'm sorry, square root from up here. And I'll pull the negative 1/4 out in front. And if I do that, I'm going to have 1/4 times the integral from 0 to 1. Square root of u in its equivalent exponential form will be u to the 1/2 du. And then 1/4. U to the 1/2, if I take the integral of that, I'll increase the power by 1. So it'll be 1/2 plus 1 will be 3/2 divided by the new exponent of 3/2. And it's going to go from 0 to 1. And also, if I take 1/4, divide that by 3/2, that's the same as saying 1/4 times the reciprocal, which is 2/3. 2 goes into itself 1 times, 2 goes into 4 2 times. So this will actually be 1/6 when I simplify that. So this will be 1/6 times u to the 3/2. And I'm going from 0 to 1. So here I can go ahead and do my substitution of the upper limit minus the lower limit. since they are limits for u. Okay, so I'm going to have 1/6 times. My upper limit is 1, so this will be 1 to the 3/2 minus my lower limit, which is 0, so it's 0 to the 3/2. Well, I know that 1 to any non-zero power has to be 1. Minus 0 to any non-zero power, that's 0. So 0 to the 3/2 is 0. 1 minus 0 is 1, so 1/6 times 1 ends up being 1/6. So in this case here, that would be the integral from 1 to 6 of the cube root of the x cubed divided by the square root of 1 minus x to the 4th dx. And here I change my limits of integration to be in terms of u. All right, now let's look at problem number 4 in this case. In problem number 4, we got the integral from 0 to 3/5 of dx divided by 25 x squared plus 9. And we're going to do integration by substitution. All right, here's what I'm going to do here. I noticed one thing about the denominator, that 25x squared is a perfect square, and that 9 is a perfect square. That's something you just got to recognize. And in this case here, I can use one of those inverse trigonometric integrations here. So here's what I'm going to do. Bring this dx over. I'm going to rewrite 25x squared by thinking about this. What squared gives me 25x squared? Has to be 5x. 5 squared gives you 25, x3 squared would give you x squared. Plus, that 9 is a perfect square. We have to think of what number squared gives you 9. In this case, it's going to be 3. Okay. So that means here, this 5x will have to be the u, and this constant 3 will have to be the a. So here's what we're going to do. I'm going to let u equal to that 5x. That would mean du will have to be 5 dx. And I got dx here, so if I want this to be dx, I need to divide both sides by 5. So that means dx will be 1/5 du. Okay. Now let's go ahead and do our substitution. I got the u, and I know a is going to be that 5, that 3, which is 3 squared. Dx would be 1/5 du. And let's go ahead and change our limits. We got x equals 0 and x equals 3/5. Let's put those in terms of u. If x is 0, then u will be equal to, since u is 5x, it'll be 5 times 0, which is 0. And then x is 3/5. Our u is 5x, so it'll be u equaling to 5 times 3/5. Well, the 5's divide out, you'll be left with 3. So this time it's going to be from 0 to 3 on our limits for u. Integral from 0 to 3 of 1/5 du divided by u, and that's going to be squared, plus, and I'll leave this as 3 squared. Okay, now let's pull the 1/5 on the outside. So it'll be 1/5 times the integral from 0 to 3 of du divided by u squared plus 3 squared. And in this case, I'll bring down the 1/5. When I integrate du divided by u squared plus 3 squared, that's going to give me the inverse tangent, okay? The integral of this will have to be the inverse tangent, because inverse sine and inverse secant have the square root in it, and I don't have the square root in it. So it's got to be the inverse tangent of whatever u is. That's the numerator. And that's going to be divided by this constant right here. That's your a. And that's 3. And this will be from 0 to 3. All right. Now, from here, we can just do upper limit minus the lower limit, because these are our u limits, our limits for u. So here's what we're going to have. And actually, I'm missing something right here. That 3 right here, that needs to be 1/3. Because, of course, we're going to have the 1/5. But we got 1 over a, which is in this case 1 over 3. We have to have that. Okay? So do refer back to that section 5.5 where you have the notes that I've given you, and it deals with the inverse, the integral of that. Okay, so to deal with that, with the inverse tangent, it's got 1 over a times the inverse tangent of x over a. And in this case, we're letting a be that 3 right here, because that's your a, and this is your a, so it's got to be 1 over a times the inverse tangent of x over a, or u over a in this case, which is your 3. And I got the 1/5 on the outside of the integral sign. That has to be included as well. Well, if I multiply 1/5 times 1/3, this will be, in this case, 1 over 15 times the inverse tangent of u over 3 from 0 to 3. Now let's do our upper limit minus the lower limit. The 1/5 is just a coefficient, so I just pull that out. And then on the inside, I just work with the inverse tangent of u. In this case, that's going to be 3 divided by 3 minus the inverse tangent of 0 over 3. Three divided by 3 will be 1. So I'm going to bring down the 1/15 times the inverse tangent of 1 minus 0 divided by 3, that's 0, so that's the inverse tangent of 0. Now we got to think of this. One angle that would give me 1 for the tangent. Tangent of what angle will give me 1? And will have to be pi over 4. So let me bring down the 1/15. So the inverse tangent of 1 will have to be pi over 4 minus the inverse tangent of 0. That means tangent to what angle will give me 0? That's 0. And then we'll do this. Pi fourths minus 0 will be pi fourths. And then multiply 1/15 times pi over 4, you'll get pi over 60 as the final answer. So that means here the integral from 0 to 3/5 of dx divided by 25x squared plus 9 would be pi over 60. And here's one more of these. This is also one of those trig functions as well, where we're dealing with trig. The integral from negative pi to 0 of sine of x divided by 3 plus the cosine of x dx. Okay, so best I can do here is let the u be the denominator of 3 plus cosine of x. And then that means du will have to be this. The derivative of 3 is 0. The derivative of the cosine of x will be negative sine x dx. And in this case here, I got sine of x dx If I want this to be sine of x dx, I'm going to divide by -1 or multiply by -1. Either way, you'll get negative du is equal to the positive sine of x dx. And I'm also going to go ahead and change my limits of integration here, because I'm going from negative pi to 0, so that means x is negative pi. So that means 3 plus cosine of negative pi is this. Well, cosine of negative pi, let's think about this. That's going to be -1. -1 plus 3 would give us 2. And the other one is x equals 0, so that means 3 plus the cosine of 0. Well, cosine of 0 is 1. 1 plus 3 would give us 4, so I'm going from 2 to 4. Those are going to be my new limits of integration. So this time, I'm going to have the integral, this time from 2 to 4, instead of from negative pi to 0. Well, that 3 plus cosine of x, that's the u. Sine of x dx, that's going to be negative du. So from 2 to 4, negative du divided by u. And I can pull the negative out in front, so it'd be negative times the integral from 2 to 4 of du divided by u. And the integral of du over u would be the natural log of the absolute value of u. So I'm going to pull the negative sign down. This would be the natural log of the absolute value of u, and we're going from 2 to 4. Now I'm going to bring down the negative sign and just focus on the natural log of u, absolute value of u, from 4 to 2. Our upper limit is 4, so this will be ln of the absolute value of 4, which is 4, minus the lower limit. Natural log of the absolute value of 2 is 2. There's a property that says this. If I have the difference of their natural logarithms, I can write that as the quotient of the, I can write that as the natural log of the quotient. So here's what I'm trying to say. Ln of some a minus ln of b, the difference of the natural logarithms is equivalent to the natural log of the quotient. So I can just write it using the quotient rule. Ln of a divided by b. So I'm going to apply that here. Ln of 4 divided by 2. And 4 divided by 2 is going to be 2. So I'll bring the negative sign down, and then natural log of 2. So my final answer for the integral from negative pi to 0 of sine of x divided by 3 plus cosine of x dx equals negative natural log of 2. Okay, hopefully this will assist you with some of the other homework problems that are in my math lab for section 5.5 dealing with the substitution rule. Again, reach out to me if you have any questions about those problems.